Okay, well, thanks everyone for coming today to our second iteration of the lectures in climate data science here at LEAP. And today we're really pleased to have the LEAP Geoscience Director, Professor Laure Zanna, as our speaker. Laure got her undergraduate degree at Tel Aviv University and her master's at Weizmann, and then her PhD at Harvard. She was previously professor at Oxford University, and then in 2019, she relocated here to the Big Apple and is now professor at NYU. And she is going to tell us about machine learning for ocean climate modeling, advances, challenges, and outlook. And yeah, thanks everyone for being here again. Looking forward to your talk.
All right, great. Thanks, Gavin, for the intro, and thanks everybody for being here online. I see a lot of people online as well, which is great, but it's also kind of nice to have a live audience. So I made the talk really, it's very much kind of, geared toward early career scientists. So, student postdocs, whether they come from climate or machine learning. So really feel free to interrupt if you have questions, if I bring up jargons. And really the whole point of the talk is to try to show you a little bit, not just the very simple picture of, oh, everything works and machine learning is going to solve everything and we're going to fix climate model, but I'll tell you a little bit about the some of the struggles that we faced over the years by using machine learning to try to improve ocean and climate models. And so I'll tell you as well where I feel, there are some advances that we can make on both sides and where I think many people can contribute no matter what their background is. So as Galen mentioned, so I'm at NYU, but I'm geoscience director, but I'm not really talking with that hat on today. I'm really kind of talking about, some of the work we've been doing in a project that many of us are part of with Pierre and Ryan and many others on trying to bring machine learning to improve climate model, especially kind of the physics part of it. So it's called M² line, and that's really going to be a lot of the work that I'm going to discuss is going to come from, many collaboration in that project. And hold on, because it's still Zoom up here, so I need to hide all the panels. Yeah. Okay, so a little roadmap. I'm going to start with a little bit of an introduction. Again, just, with telling you a little bit what climate simulations are, what model errors are, why do we care, what do they matter, and talk a little bit about missing physics, which is what we're going to try to capture with ML. Then, of course, how can we fix it, right? How can we fix those model errors? How can we improve climate models, in quotes? And so one possible solution is to use data, machine learning, and physics together, try to bridge the gap between those things. And this is what we're going to talk about. So as I said, my goal is really to try to illustrate some of the specific examples that we learned over the years with pros and cons. As I said, I'm going to tell you things that didn't work as well, and where contribution from data and machine learning and climate scientists are needed. And so going to identify some of those problems and tools that we developed that might be of use with many people in this room, I hope, and anyone from the LEAP community and others. And of course, the work is in collaboration with many great people, especially kind of former students and postdoc, Andrew Rust, Tom Bolton, Pavel Perez-Hogan, and Ziwei Li, and many other collaborators through MSCOP Alliance. Okay, so I'll tell you a little bit about myself because technically, those are our LEAP kind of faculty meetings, right? So, and since I'm the LEAP Geoscience Director, you should know who I am. So as Gavin mentioned, she talked about my degrees, but I'm really a physical oceanographer. So I work on trying to understand how the ocean works and how it works within the climate system. And so this movie here showing the warming of the ocean in the past 150 years. And so it's kind of, a reconstruction. So where it pops and it's kind of yellowish, it's where a lot of the heat has been taken up and stored by the ocean. So there's a clock up there that goes from 1870 up to present. And you can see kind of, some places highlighting, right? So say the North Atlantic is kind of, popping up quite often on a weird time scale. The Southern Ocean down there is another place. And really most of my work is trying to understand how the ocean takes up heat, why it warms, how it moves the heat around, same for carbon and oxygen, and how the ocean also influences the atmosphere. So really trying to think about the coupled climate system. So that's been driving my work, for a long time now, really trying to understand how the ocean works, how it impacts the climate, but also how can we model it, okay? So it's a big source, it's a big sink of heat. We're trying to understand how it works. And that's really what motivated, most of my research. And kind of trying to understand how the ocean works, slowly brought me to trying to understand how climate modeling works as well, because a lot of the work that we do involves models, involves simulations of the climate. And so in Oxford, I used to actually give a talk on climate modeling, and then use 3 quotes to try to illustrate a little bit of our philosophy. So the first one is a quote from George Box, which many people see the second part of that quote: all models are wrong, some models are useful. Kind of like the first part of the quote. The most that can be expected from any model is that it can supply a useful approximation to reality. So it's only an approximation. Everything we're going to look at is going to be an approximation. We're not looking for the truth necessarily. We're looking for something that can help us understand how the world works. And for us, the world is going to be the climate system. And so kind of a simple way to think about it, it's not about having the perfect answer, but having something useful that you can work with. The second one is kind of an interesting one now that I work with data, from Samuel Cannon, another mathematician, saying the purpose of the model is not to feed the data, but to sharpen the question. So you could almost say this is a paradox, right? We're going to talk about machine learning and data-driven models. How is it that it's not what we're trying to do? So I actually see data science as a way to sharpen the question, right? So you are taking data where you have a lot of information and you try to come up with the simplest possible model to explain the data set that you have. So, and of course, whether it works or not, it is a scientific, advance, because if it didn't work, that means your hypothesis was wrong. If it does work, then you need to scratch your head on why did it work, right? And that's a way to sharpen the question one way or another. Second one, it's not from a scientist, but it's basically from Paul Anderson, which says, I haven't yet to see any problem, however complicated, which when looked at in the right way, didn't become still more complicated. It's kind of the way I think about climate models and the climate system in general. And so we're going to go through that kind of a little bit of a roller coaster of feelings about different models and different ideas as we bring data, models, and physics together, try to explain a little bit how we can bring machine learning and data. So as I say, I'm a physical oceanographer. So the ocean is composed of many scales, right? So going from the left here, relatively small scale where things dissipate, so they can be quite small. What we're very familiar with is the right-hand side of this plot here, which is the basin scale ocean circulation. So it's really thousands of kilometers. It's driven by the wind and buoyancy gradient, meaning heating and fresh water, and drives the large scale ocean circulation. That's what transports, many of our tracers in the ocean. And then as you go towards the left, then you have smaller and smaller scale. Mesoscale eddies over here, 10 to 100 kilometers, are basically deriving, if you want, their existence from the large scale flow and its instability. They're kind of turbulent features, and they actually extract a lot of energy, but they also a way for the ocean to transport heat, carbon, and other tracers. So they play a pretty big role in the ocean circulation, and many people in this room are experts in mesoscale eddies, and there's a pretty good reason for why, is they're really order one in understanding how the climate works. Yeah, they play a big role on where heat is being taken up and how. And so this is kind of really a big part of the problem that we're going to go after, is this idea of the mesoscale interacting with the large scale fluid. If you can't resolve them in a climate model, then you're going to miss a big piece of how the ocean works and how the climate system works. And so, movies are always good. So this is a movie, so it's a little bit slow. I think it's probably because of the connection. So this is a climate simulation from the GFDL group. So it's a simulation run, it's a coupled climate simulation run at 10-kilometer resolution. So basically you have a bunch of little boxes, one basically 10-kilometer by 10-kilometer horizontal resolution, and it solves the full equations for the ocean, atmosphere, sea ice, and so on. And here what you can see is the sea surface temperature. So kind of pretty amazing, right? You can see the Gulf Stream detaching, from the US East Coast. You see a lot of kind of turbulent and filaments popping up everywhere, and they come from the instabilities of the. And again, they're quite important in taking up, in basically steering and mixing different tracers in the ocean. But this is really how climate simulation works. We take super complicated equations that we can't solve by hand. We break them down into pieces, okay? And so you have a little example here on climate model grid, right? So we break down into pieces, and in every one of those boxes, we try to approximate the equations that we have. But of course, the physics that you can resolve and all the processes that you can resolve is limited by the size of the grid box that you have. So this is going to be your limitation. Anything that is happening below the grid box size that you have is not going to be resolved. Okay, and that's one big problem for us. And the fact that some of those processes are not resolved and the fact that the equations are only approximate means that the models are what we call biased, meaning they have errors in them when we compare them against observations. So I didn't want to pick and choose one model. I picked three. So it's not, I don't have a favorite. So I don't want to complain about one modeling center. Three models. So three different climate models, basically developed by three different modeling centers on this plot here. And we're showing the sea surface temperature. So the surface of the temperature of the surface of the ocean minus that of what's observed. Okay. So basically, if you had a perfect model, hopefully the error will be zero. So in temperature, and so this is the color bars that we have here. And you can see this is clearly not the case, right? So in some places, the models are warmer or cooler by 5 degrees. And so those are pretty big numbers, right? So the largest temperature that you could get are about 30 degrees. At high latitudes, it's much lower than that. So you end up with errors in your simulation compared to observations that are quite large. And again, what's interesting is if you look at those three models, some of the errors are actually identical, right? So let's say in the North Atlantic over here, you have this, blue blob here that is a pretty common error in many generations of climate model and still shows up. And one of the reasons is actually ocean processes not being properly resolved there and the coupling between the ocean and atmosphere being older one. And so just to show you again in picture, model error will come from all the missing physics. So everything that is happening below the green box size of the climate models. So those turbulent eddies that I showed you before, clouds, radiation, all those things are actually not resolved on the grid of the climate models that we have. And the second thing is, of course, numerics, right? We had, in the math world, we had continuous equations that technically you could solve by hand, but we can't because they're just too complicated. So we've approximated them on the grid. And so those approximation also leads to error. Okay, so those are two basically reasons that we have errors in our simulation. One is approximation of continuous equations onto a discrete grid. Another one is anything that is happening below the grid box size is not resolved and need to be approximated. Okay, so I showed you what I call bias or errors in simulation compared to observations. Now, is that it? If I run the model into the future, I don't know what the future looks like, right? So we have no clue what the future looks like. So if we basically pretend that we're going to have a given emission scenario in the future, how the climate models will respond to that. Okay, so the different climate models all get the same forcing in quotes. And what we can show is if we plot sea level as a function of time and look at the projection, so look into the future, the shading that you see for a given color is going to be different run of different climate models filling the same forcing.
So what do the different lines represent?
So different lines, different climate simulations, different climate models, okay? Like before, so I showed you only three, but there are many in the world, right? So there are many climate models. So over here, that's the historical period where we have true measurements. And so you can see already the models are a little bit all over the place. And then when you go into the future, then they continue having a relatively large spread. So this kind of, spread between different models continue into the future.
So you picked two lines from the left-hand side and projected them over.
Yeah, so they continue. So each line is a climate model. So over the historical period, we know what the forcing is, and then you continue them into the future with an additional forcing.
Right, so there are more lines on the left-hand side where you have observation, but when you, in this file, you only have two projections shown.
Okay, that's a good question. I should have, let me explain that again. Each color is actually a different scenario, so it's a different forcing. Okay, so the blue line is a weak forcing, the red line is a strong one, and then the shading are actually many different climate models. So for a given scenario, you have a given color, and then the spread is going to be the different simulations coming out of that scenario, right? So you have as many lines in that kind of red shading that you have in the blue shading, and that you have here over the historical period. Yeah, thanks for clarification. Any other questions?
So are they all forced to agree like around year 2000? Is that because the observations are really good then? So they're
okay, so that's a good question. So every time that you look at something, usually we do them relative to a given period, and they took at that given period, that's your reference state. So everything is going to be centered around that line, and then the spread is going to go from there. So that's completely arbitrary. You could pick a different date. We like to pick usually recent periods because observations are better. So that's kind of a nice way to calibrate it. Yeah, that's a good question. Yeah. Anything else? Yeah.
Sorry, can you just explain a little better the two scenarios of models and outcomes?
Yeah, so basically the amount of forcing that is going to be put into the climate model, right? So the different amount of CO2 aerosols and so on will give you two different projections because different greenhouse effect will have different warming. And here we're really looking at sea level in the ocean. And the reason that sea level is going up, right, is going up for 2 weeks. So, well, multiple reasons, but mainly over that period. And in those simulations, one is because the ocean is warming, so water expands, right? So basically sea level is going to go up. And the second reason is melting, right? So basically melting of ice sheets will be the second reason.
So potentially you could have made the same visualization on the left-hand side when you have a real data, also group the lines into the red and blue.
So in the real world, but in the real world, we know what the forcing was, right? So it's no difference in our, I mean, in good, we have a pretty good estimate of what the forcing were. So for the historical period, we're pretty good. If you were thinking about paleoclimate, for example, right? So that could be another way to think about it. The forcing is known, but as a number. So would be a possibility actually to think about different trajectories. Any other questions?
And
Oh yeah, I like questions about it.
the
It's a lot more fun.
For the future, the forcings could also be simulated by other parts of the climate model.
Okay, so here, okay, so that's a good question. So right now in those simulations, so the forcing is really kind of, you know, externally forced, so kind of CO2 and so on and so forth. Now the current climate models are playing out with new things. What if we melt out of Antarctica, different depth? So that's a different type of forcing that is induced, you know, by increasing greenhouse gases, but the models don't do that properly because they don't have active ice sheets. So can you actually mimic that? And so that's, yeah, so that's another type of simulation. There are quite a few out there. Yeah. Okay, great. So now let's continue on our path of trying to understand what's resolved, what's not in the climate model, and how can we fix it. So this is the same climate model I showed you the fancy movie from earlier, right? That was run at 10-kilometer resolution. And so now same equations, so to speak, right? So same ocean equation. We're still looking at surface temperature in that plot, but now the model is run at 3 different resolutions. So the one on the right is the original one, 10-kilometer resolution. The one in the middle, it's run at 40-kilometer resolution. So now your grid box is much larger, right? So that means processes that are below that scale are not resolved. So you can see it's getting smoother, right? It's getting more viscous. If you go to the one on the left, so now it's a grid box of 100 kilometer by 100 kilometer. So the one on the left and the one in the middle is roughly the resolution of the current generation of climate models. Okay, so they're quite viscous, right? They're not as turbulent as the one you have on the right. And the fact that you're missing all those filaments and turbulence, it's not just that your movie does not look as good, but it's, again, you're missing important and critical processes that are mixing part of the ocean. They interact with the ice, actually. They do have a direct impact on how much ice you can melt. We're around Antarctica over here. And I stole that movie from Julius, actually, quite a long time ago, and I always show it. It's one of my favorite animation to talk about resolution and climate models. Okay, so now the fact that we can't resolve those processes, again, does that mean that it's the end and we don't do anything? So the way we've been doing, you know, what's called the parametrization of the closure problem, which is representing all the processes that are not resolved in the climate model. So again, up here, you have clouds, you have radiation, you have, you know, basically boundary layer processes and so on. And in the ocean, all the turbulent mixing processes that I told you about. So we need to come up with a representation for them. So we need to come up with a way to capture the effect of those turbulent features or cloud on the large scale quantity of the climate system we care about, say temperature or, you know, precipitation and so on and so forth, as a function of the things we know, or the function that the model can resolve. So only on the grid that you have at coarse resolution. So, you know, that's been the business of, you know, climate modeling and parameterization for decades. This is not new. It's been going around for quite some time, shown some great improvement in, you know, different parts of climate models, but they the traditional closure of trying to come up with mathematical approximations have still shown us that they still lead to uncertainty at the end of the day, both in present day climate, but also in future projections. So the question is, of course, can we do better, right? And that's kind of one of the big parts. So what I'm going to focus on is one example of those ocean turbulent eddies that I told you about before. So again, kind of same ideas, right? So if you run a simulation at relatively high resolution, you have all those turbulent features over here. They're going to be a pretty important player for the climate system. But the majority of our climate models are run at those kind of coarser, more viscous resolution. So what can I do to capture the effect of those, smaller scale turbulent features onto the large scale, so it gives me the same physics. So just want to make one comment is I'm not trying to make this picture look like the one on the right, because I'm not trying to, create fake images. I'm really only trying to capture the force that those turbulent features have on the large scale fluid. And so it's our, kind of, if you think about Newton's law, right? So you're basically trying to apply an additional force so you can accelerate the currents or that you can increase the temperature, but you don't necessarily get more structure in your image, so to speak, okay? So again, just to show you a little bit, this kind of spread that comes out of those ocean eddies. So this is kind of a very specific, quantification of how much heat goes into one part of the Southern Ocean in different climate models. So on the x-axis are a bunch of different climate models. And on the y-axis is the amount of heat that we have. So the total is the black line. So for a bunch of different models, you can already see that the total heat that goes up is quite different. It can change by a factor of 2 or 3. Okay, so that's not good already because, ocean warming means sea level. So different model can give you a factor of 3 difference in the amount of sea level that you would get. Now, what's it, the red dots is what's actually resolved by the equation, meaning things that we didn't approximate. So things that are not below the grid box size. And you can see they're closer to 0 than anything else. So what the model resolve actually has almost no contribution on the amount of heat that the ocean is taking up. And all the other dots, and I'm not going to explain what they are, but they're all related to those turbulent eddies. They are the ones that actually contribute to most of the heat uptake, and they're the ones that contribute to most of the spread. That means that everything that is parameterized, everything that has been approximated in a kind of ad hoc fashion, both the driver of uptake, but also the driver of the spread, meaning that that's the thing that gives us different answers. So really kind of trying to narrow this down, coming up with an approximation that are better, and also reduce that spread is definitely an order 1 problem when it comes to climate models. And that's really what we're going to do. We're going to focus on this part, right? So trying to represent those mesoscale eddies that contribute to the heat uptake and how they transfer energy and how they affect the large scale transport by using data. Okay, so how can we do that? Well, we have data. The data come from simulations in our case, right? So because in many instances, we have a lot of simulations that we can run either in small domains or, some of the simulation I showed you before that climate models have run, but they're not typical. But we still have data, right? So in our case, we have equations that we can solve, and we can simulate a lot of data and generate a lot of it. We have new algorithms, all right? So those algorithms are great to capture complicated relationship from data. And basically what we're going to learn is this closure, this parameterization that tells me what is the effect of those turbulent eddies on the large scale fluid. So I'm looking for force. So basically, if you were thinking, the eddies are kicking the fluid, I'm looking for that. I'm looking for the, the kick that the eddies are basically doing on the large scale fluids, on the large scale equations of motion. Lots of people have been working on this, right? On this problem of using machine learning with data to come up with a new closure, so a new representation of processes that are not resolved. Many in the atmosphere and the ocean, again, many people in this room have definitely kind of, been leading the field in those areas. And so I'm gonna, rather than tell you again, as I said, only what works, I'm gonna try to show you a little bit what doesn't as well. So we've been working on that with, people in my group for quite some time. We started, I think, in 2016 or 17. We did a lot of stupid things early on. We still do, by the way, but we got better. And then, the few first talk that I gave on this topic, I used to come up and, show really an in-depth study of something super important, and I used to make conclusions at the end. And I gave a few of those talks, and then every time then I try something in a different model, then everything I said the year before actually was wrong. And so I could keep on doing that for a long time. I think it can work, but rather than continuing, we decided to pause for a second and take a little bit of a step back. And I'll show you a little bit first what we've done and when we decided to stop. We probably should have stopped before. So input data, we use data from pretty much any model that you can come up with. Some that we build in-house, some that were existent, very complicated, very simple. We thought that it was one of the biggest challenges, and it still is, and I'll come back to it. Methods, pretty much any flavor of machine learning algorithm that exists, we probably try some kind of flavor of it. Some deep learning that has basically thousands of parameters that can capture very complicated relationship, to things much simpler like regressions, sparse regressions, and things like that. I'll show some examples. We try to build closures that are deterministic, meaning you have a one-on-one mapping, you know the input, you get one output, or probabilistic. A given input, you learn a probability. So you learn basically multiple outputs in one go to try to represent the uncertainty. We tested it on different climate regimes, so where you have different CO2 forcing, different Reynolds numbers. So the Reynolds number is a way to represent turbulence, right? So a way to quantify turbulence. So very different level of turbulence and different configuration. And we implemented it because when you learn the closure, you need to go and put it back into a coarse resolution model. We did simple, complicated, and so on and so forth. And as I said, I think pretty much every paper that we wrote, after we wrote it, then we tried something else and everything was wrong. So we decided to go back and go to basically the bread and butter of kind of simple model of turbulence to try to capture that captures most of the effect that we have. And we settled on PyQG, which is a model that was developed by Ryan and others. It's open source. It really kind of captures most of the physics that is necessary for us to have. It's also very flexible. It's in Python, and you can do a lot of stuff with it. And so really our goal was, let's not try to find the best parameterization, but let's actually try to find a way to understand what we're doing, right? So really trying to focus on physical mechanism and interpretation in a simple framework, test robustness of the method and the results, how much can we push the ideas forward, and also have something that, is verifiable and has some uncertainty quantification. And so here you have kind of, those kind of turbulent flow field that you can generate with that model. It's very cheap, and you can do a lot of stuff with it. And the goal was really to try to develop data set metrics and benchmarks for us first to understand, but also to hopefully give to the community. So that's going to be the motivation. Take a step back, trying to look at what we learned. So how do we do that? So we need to consider two steps here. Okay, so we're going to generate data from this kind of very simple turbulent model, and we're going to learn a closure. All right, so we're going to learn that kind of missing forcing that a coarse resolution model should have if we want it to behave like a high resolution model, but without the computational cost. So we're going to have some input that come from numerical simulations. We're going to use some machine learning algorithm to try to learn this missing turbulent forcing that we want to put on the right-hand side of a coarse resolution model. So that's step one, right? So step one involves machine learning. The data is there, we've generated it. We're gonna, learn what's missing from a coarse resolution model. And rather than do it the way we've been doing it for decades, which is, oh, I know that turbulence should do X and Y, let's write a mathematical operator. We're just gonna ask the data, what is, this forcing should look like? Or at least how can I best represent it with machine learning algorithm? Now, when I have it, then that's not the end, right? When I get that forcing, now I need to make sure that if I put it on the right-hand side of a climate model input, for us it's PyQG, run at a coarser resolution, well, it should improve the model, right? So that's the goal. So step two, when we have this new forcing, we set it aside, we saved it. We're going to take our simulator, our climate simulators at coarse resolution. We're going to run it with this additional forcing, so this additional kick that comes from the turbulence that is not resolved. We're going to get an output. This output here, hopefully, is better than the output that I had before, which was blurrier, but at the same resolution. Does that make sense? I'm going to pause for a second. Yeah? Great. So first part, we're going to learn the missing forcing with machine learning algorithm. Second part, we're going to plug it in a coarse resolution model, and cross our fingers that we actually do better than the coarse resolution model by itself or a coarse resolution model with an old parameterization. So let's start with step one in that very simple model. So some of the things I'm going to tell you can be not the most exciting thing, but we actually realize were the most important one. First is, how do you calculate this missing forcing? So you need to basically filter and coarse grain your data. So it's quite boring to some extent, but it's actually a pretty important step. Because the way you're going to do that, you're trying to actually extract what's missing from something at coarse resolution compared to a high resolution field. So don't bother with the equation, but at the end of the day, we're looking for something that is basically the difference between two nonlinear terms, which are not easy to calculate. Now, how do you filter and coarse grain? Well, there are many options. And interestingly, so here I'm showing a field of what's called potential vorticity. So it's basically a combination of two quantities, so to speak, one that is related to the velocity and one that is related to the stratification in the ocean. So it's a nice way to combine dynamics and thermodynamics in one variable that is conserved in the ocean. So here we're filtering this field, this high resolution field, onto a coarse resolution data, which is what we're looking for. So we have three operators. I'm not gonna bother on telling you what is what, but each one of them, I mean, at the end of the day, by eye, they kind of look the same, right? The pictures look the same when you do it on the vorticity field. Now, that's not what I'm trying to get. Right? I'm trying to get this kind of missing forcing over here. So now I'm gonna try to look on what's missing, right, at coarse resolution for a field to actually have the same properties as high resolution with those three operators. And that's the field I'm getting out from the three different operators. So I'm calculating the same quantity, except the bar that I have over here is a slightly different filtering operation. So the missing forcing that I call the truth actually depends on how I do my filtering. So this is, again, this is not the most exciting thing on the planet, but already tells you that the first step that you're gonna think about is really what is it that I'm looking for? What is the true missing forcing? And what I'm going to learn is going to be one of those. And we're going to see that there is a sensitivity when we plug it back into a climate model on how we do it. I see Ryan making a face.
It is the most exciting thing on the planet too.
I know. But I think a few of us are on that camp. I'm not exactly sure that everybody is with us, but hopefully I'm motivated enough that it is the most exciting thing on the planet. Okay, so we have three possibilities, right? Still a missing forcing, still technically something I should put on the right-hand side of the climate model, so something I should learn. So now let's try some machine learning algorithm to learn this missing forcing. So one test is a good old neural network. So complicated deep learning, convolutional neural network. The inputs are going to be the fields that I mentioned before, those potential vorticity fields. You can think about them as velocities and temperature if you want, same thing. Many layers. I don't want to really talk about the architecture because you can play with that as much as you want. Then the output is going to be our missing forcing, right? What we're trying to learn. And so we're going to minimize some kind of loss function to try to find the best representation with a convolutional neural network of that missing forcing. You can build in physical constraint to make sure that everything is conservative. So you can do a lot of things with neural network nowadays that you couldn't actually many years ago. You had to hack them. Now, actually, packages have evolved in a way that we don't need to hack things anymore. And so we can build physical constraint in a simpler way. So that's one option, right? So neural network, you're going to end up with thousands of parameters. They're really good at capturing very complicated and complex relationship of quite textured data. Now, the small issue I have with them, I still like them a lot and I use them a lot, is it's very difficult to interpret, right? I end up with thousands of parameters. There are some methods out there. For the subgrid parameterization, we haven't been able to really extract any useful information from them by themselves. So another option that we've done was trying to actually learn directly equations from the data. So here is one example of that. I'll show you an example later on. So one is genetic programming. And so this is a symbolic, algorithm. And the idea is you try to evolve some kind of, random expression initially to learn this missing forcing. And so basically you're trying to mimic evolution. So you're going to have a bunch of trees, right? And so the algorithm can take multiplication and addition and things like this of the different, data that you give it. And it's going to try to come up with a simple expression. So a parsimonious expression that has very few terms that will try to mimic your eddies. So basically, again, in a very, very crude way, it's going to try to learn an equation that can describe your missing forcing given the input data. So it's pretty powerful. It's been used in many examples of physics, and I know Carl used some of that to try to kind of get some understanding of more complex model. People at Columbia have developed some of those methods based on genetic algorithm, try to learn laws of physics. And so the question is, can we learn a new parameterization from data with this type of algorithm? And of course, the big question mark is, can we learn new physics as well? And I should clarify, when I say learning new physics, quite often the operators that you get are the ones that right? Because we're not reinventing math. But can you understand better how the scale interaction is actually working? How the energy is exchanged between different scales that you're trying to capture, how dissipation is changing in those closures. So it's kind of a different way to actually ask something about the physics. Now, the slight issue with those type of algorithms, they are not made for the problems that we're after. So one issue is that they know nothing about spatial scales. And we need derivatives. We need spatial derivatives, right? So we had to build in something about spatial derivative. For this case, it was very easy because it was done in spectral space. So it's just multiplying by a number. But we've actually now changed the algorithm to work in real space as well. So you still need to have those algorithms to work for physics problems. So that's always one thing to keep in mind. The second thing is it's still an algorithm. It does not know physics. So sometimes it does some silly things, like it's going to add two quantities that have different units. That's not good, right? I mean, this is the first thing you learn in school, check your units. That tells you if you made a mistake. So we had to basically kind of try to hack this as well in a way that we can actually stop the algorithm when it does something that is absolutely not physical. And so we do it as an iterative manner. But the idea is you come up with an expression. I'm not going to talk about the physics of it, but you come up with an expression that hopefully you can interpret and talk about the physics. So two different types of model, one that is pure deep learning, thousands of parameters, another one that has fewer parameters and that you can hopefully interpret in a mathematical way. So now step two, right? So I learn models. I need to plug them back into a simulation as well, right? So they need to do well, both offline, so when I learn them, and then when I plug them back in. And so one of the characteristics we're looking for is we're looking at kinetic energy as a function of time. The gray line is the coarse resolution model, and the black line is the high resolution model. So you have more energy in a high resolution model than in a coarse resolution model. And that's what we're trying our machine learning networks to do, right? We're trying to energize the fluid. So this is really what we're going for. So I'm going to show you two sets of tests. One that is offline, so meaning before we plug it back into the climate model, just to see if the machine learning algorithm, the machine learning models that we learn are actually good, right? So that's kind of step one. So hypothetically, if I were to plot error versus complexity, I would expect a model, with thousands of parameters to probably give me a lower error on what I'm learning than a model that has only one parameter. Right? So if I have a very complicated, function, and I try to come up with a linear approximation of it, well, probably the error is going to be pretty large if I'm trying to capture something from a nonlinear function, right? So the error is probably going to be large if I just come up with a linear approximation of it. So again, hypothetically, if I were coming up with a physics parameterization, it'll probably look like this. You'll have one parameter, and if you were looking at how it matches with the missing forcings, we probably have low correlation. And then when you go to a neural network, you probably have very high correlation. And if you have the data-driven, equation discovery, you're probably somewhere in between because you have quite a few. And this is exactly what we find offline. So here are data-driven parameterization and the metrics based on what we learn. So here's the neural network. So we have R squared and correlation. So when you have a high score, that means you're doing well. So the neural network, basically 0.9 and above for everything. So it does really well because you give it tons of freedom to learn something. Okay, so amazing. It learned what it's supposed to learn. The symbolic expression, all right, lower, right, but still pretty good. So, you're still going down in terms of, the error, but, still does pretty good. If you look at the physics-driven one, it's terrible, right? Just offline, like it really off. And that's all offline, right? So right now, you could say, if I plug that into a climate model, then technically the neural network should be superior to the symbolic expression to the physics-derived parameterization, right? So that would be like a first guess. Now you can guess, it's probably not gonna happen, right? So here we are. So now we took those three models and we run three simulations. So this is a high resolution snapshot. This is the low resolution, so less kinetic energy. It's a little blurrier and things like this. Now we took the same PDE, so the same equation with the same resolution of this coarse resolution model, and we add that forcing, that new forcing that we learned. So over here, this is the physics-based parameterization. In the middle, the one with the neural net. On the right, the hybrid symbolic expression. By eye, they all do well, right? Even though offline, I would have said the physics-based is going to be a disaster. So clearly, that does not correlate very well. So that's one thing. If I look at other metrics that are more physics-based, so rather than eyeballing, right? So I'm still eyeballing, but not in a snapshot. So again, the kinetic energy I showed you before, black is the high res, low res is the gray one. Every single one of them gives me roughly the high level of kinetic energy I wanted. Now, they're not all behaving the same way, right? The neural network shoots off like super fast. So it seems that its timescale are much faster than kind of the more, equation-based one. So capture something different about the physics, or it just, tries to go too far, too fast. If we look at a different metric, say the distribution. So quite often we're interested, right? If we're thinking, rather than thinking about turbulence, we're thinking about the climate system. We're trying to understand, extreme events, right? In temperature or precipitation. So we like to look at probability distribution function in that case. So here's a probability distribution function of the variable that we're considering. So the gray one is again the coarse resolution one. The black one is the high res. So the high res are longer tail, meaning more extremes. Now in this metric, they're not all equal, right? So basically the neural net does better at the probability distribution than the equation-based one. So depending on the metric that you're considering, you can start seeing some differences. And here it's eyeballing only. Yeah.
You might be getting to this, but does it also, so if you use a different lower resolution, like if the box size was different, would that also change which one was better?
Yeah. So we did all of that. Yeah. So I'm not going to show any of that here. I think I can remember if I have that slide. But yes, there is a sensitivity to the resolution on which one does better. And actually, yeah, I'm going to talk about generalization in a second, not for different resolution, but for different physics. So there is definitely a sensitivity, but one of them quite often perform better all the time compared to the others. I'll get to that in a second. So eyeballing, pretty good, overall, but some are better than others. So my point again, offline correlations, right, and things like this do not directly translate into online performance. So now there are two options. Either we actually picking the wrong offline metrics, which that's my view, I think, or really it's magic. And I don't think it is magic because I do think it is capturing something that is real. We just quite haven't found the right metrics offline.
Yeah, so question about the kinetic energy plots. The one that shoots up really quickly is neural networks, right?
Neural network, yeah.
Because neural network is trained on some statistical equilibrium solution, and then it suddenly saw a ramp up phase, and I'm like, oh, what am I doing?
Yeah, so that's a great point. So we thought the same, but we actually give it also data from the transient part, and it still shoots off. Yeah, but great hypothesis, but yeah, didn't work. We thought the same. Yes, it has something else that I don't know. It likes to be fast. So one thing again that I say we were kind of speeding up and looking at stuff and coming up with hypotheses is one thing that we've learned as well is do not just eyeball. Right, this is kind of one thing that I've learned, and I learned it actually from some of our postdocs that came from computer science. Like, don't just eyeball. Come up with a real metrics of things that you really want to compute, and do it in a careful way. And so for us on kind of the climate side, there are many metrics we can think about. So usually when you're trying to improve climate models, there are two steps. The first step, and I would say that's my personal bias, is I want to improve physics. Okay, that might not translate into improving model error, but I still want the model to actually get the physics right. And so for us, getting the physics right is getting this kind of weird quantity which is the flux of kinetic energy from small scale into large scale. So this kind of weird curve that you have here. So in a high resolution model, this curve has a higher amplitude, meaning we take energy from the small scale, from the turbulent features, and we push it upscale. All right, so that's how the small scale influences the large scale. That's really what our closure is trying to capture. And so, well, rather than just eyeballing two curves, we can come up with a metric that actually computes the distance between the two curves. So there's a simple score, right? Simple similarity score that actually computes if you're doing well, and especially when you want to compare with many models. You want to have something that is robust rather than just eyeballing things. So that's metric number one, right? And that can be one of them. There are many of them. Each one of you, for your problem, you should think about what's the physics you're trying to improve and try to compute what's missing. Now, again, as I say, when you improve physics, you don't necessarily improve the climate models, and climate model developers know that also well. Usually when you fix one thing of the physics, you usually break about 20 others, and you don't necessarily improve your climate simulation. But we still aim for it, right? So the second thing is you want to improve the direct variables that you care about. As I said, the distribution of precipitation over North America, or the temperature over Europe. So here's another way to calculate metrics on improving variables, is you can calculate basically differences between probability distribution function, right? So there are many metrics and distances to compute that, but that's another score that you can think about. And of course, you can have many of those axes, right? So you want your parameterization to capture as many of those metrics as possible, depending on the problem that you have and that you're interested in. So now let's try to look at performance, right? So we took all those parameterization. So let's take a step back for a second. You remember we had three different types of filters, right? So we have three different ways to compute the parameterization. We can also play with the type of input that we put in, right? Different, different fields with their gradients and so on and so forth, and trying to learn, this missing forcing. And we're going to measure it in two ways in this kind of axis. So when we go up here, this is going to be really, really good, and we're pretty happy. When we're down here, it's really bad, okay? And we're going to, in those two axes, one is going to be how well do we do for this physics aspect, right? So how much do we capture this transfer of energy from small scale to large scale? And over here, how well do we actually capture the probability distribution function and the extremes after we plug in? So again, let's see what happens. So it's going to be 100 and something simulations. You're going to see a lot of dots, all right? So three different neural network with the three different type of filtering. This thing that is called backscatter, this is the physics-based parameterization that was developed about a decade ago. That does perform very well as we saw. And then a couple of hybrid ones that we came up with. So data-driven equation discovery. Okay, so first, huge spread, right? So let's start with that. Some of them are terrible down here. Some of them do quite well. So a few things that I want to point out. So one of them, the sensitivity to the filtering is huge. So if you look at the different colors, right? So green, red, and pink. So the pinks are all over here. Then the green are all up here, and the reds are all up here. So each one of them has slightly different inputs and different constraints. But really, you can see the three clouds of dots, which are three different filters. So one filter is better than another. And that's kind of pretty much a given, without even changing anything about the architecture. The type of filter that you use can already kind of tell you on which part of that plot you're going to be. If you're going to be down here or over here. Sadly, for quite some time, we've been using this filter that puts you over here. So it was a good thing that we stopped and start to rethink a little bit how we do our filtering. So that already tells you that. Then, of course, the input that you're going to use can give you a huge range of spread, right? So it can give you a huge range of performance on how well do you do in improving physics and improving the variables that you care about. So this first step of really learning or figuring out what you're trying to learn can have a pretty big influence on what you're looking at. And of course, we can only do those type of tests in simple models, right? And that's why we took a step back to actually be able to actually pinpoint and develop this new sets of metrics. Now, if we look at some of the physics-based parameterization and the data-driven one and one of the CNN, we have quite a few of them that perform extremely well up here. Okay, so the ones that we saw before, they do quite well, and we're pretty pleased with them. But again, you can get things that are really poor. Now, is it done? Is it over? Well, we need more tests, right? So one more test is what happens if we keep the same closures that we've learned from a given configuration, right? Given equation, we learn our closure. Now we want to plug it back onto the same model, but same physics, but a little difference into some of the parameter of the simulation. So in the ocean, with the same equations, you can get different type of regime. Things that look a little bit isotropic with lots of turbulence, and things that have lots of turbulence, but also structure. So jets, right? So those two solutions are solutions to the same equation with slightly different, tuning of parameters, so to speak. So now the pictures are very different. So this is our high resolution, our low resolution, that is, you can barely see any jet, there are no turbulence. Now this is the low resolution plus the physics-based parameterization. I see no difference compared to the close resolution, right? Seems to have made nothing, no improvements whatsoever. If we look at the neural network now, it's a disaster, right? It was one of our top performing one, but now it's actually trying to behave like a homogeneous turbulence type feature. So basically try to overdo it. So, that's, one big problem. The hybrid symbolic expression, so the equation discover one actually does quite well, still under that. So more robust, right? Only a few parameters by learning this equation discovered one, but definitely more robust different regimes. So less parameter, you might not get the best scale offline, but you might actually have something that is robust across, different scales. So I have no idea how many on time. Yeah, okay. So let me close with a few thoughts, because I think I'm at the end. So, there are a few things here that we can say, right? So framing and setup is very much paramount, right, to what we're doing. So always taking a step back and thinking about how do you want to frame, your problem, how you want to think about it. And so again, the right variables and the filtering. So Ryan was saying a few of us are interested. So there's a package, GCM filter, can help you if you use ocean models with, geometries and so on to actually deal with these filtering issues and how to do it. Physics constraints are pretty important, but they're not enough, right? So developing new tools is going to be very important. And so that's why this kind of, dialogue between different, community is super important. And that goes back to the point about robustness. Data set evaluation and metrics, I believe they have to be vast and robust. And so again, every time we have to step back, try to think about what is it that we're trying to improve. And it might not be the same for, for the problems that you're going after. And one thing I haven't shown, and I'm not going to show it because just I'm running out of time, but mix and match actually works. Meaning that if I learn a parameterization with a given data set and I implement it in a different model, which was not the same model I trained on, we actually find that it works. To say the only problem is you need to retune everything quite often. And so the old problem are the same as the new one. So the new ones are the same as the old problem, sorry. And so that means that, there are a lot of tuning and a lot of ideas around tuning that are going to be pretty important. So just, I'm going to skip the implementation in things, but I just want to say a couple of stuff. So I mentioned earlier that, we had a large project called M²9, and, part of that project has been really trying to find also the right balance between, machine learning, physics to improve climate model. And I think it's going to take, quite some time. And that's why we need a community for it. So I just wanted to, bring up a couple of stuff that might be helpful to some of you. So one of them is, how do you move forward as a community when you speak different languages, right? So one thing that we tried to put together was this Jupyter book that, was developed by the team members, PIs and early career scientists that goes literally through our proposal, which is how do you come up with machine learning parameterization using data? And here really the goal is to teach machine learning experts what a parameterization here, what a climate model is, what a numerical scheme is, and also the climate scientist, how do you train a neural network? How does it work? How do you play with it? So this is all online and open source, and you can use it, and hopefully it might be useful for those of you who actually try to learn one piece of that problem. So I think we do need a common language, and sometimes it takes a little bit of time, but I think it's worth it. Other tools that we have online is all those machine learning algorithms and trained models, right? So we're trying to put them out there. So they're on GitHub. And so, I think it's very important for people to learn how to leverage many of those tools. So whether they're ours or somebody else, right? But quite often it requires a little bit of work and effort. So again, making sure that finding the right connection across different community, I think is going to be very important. And hopefully some of the focus group that will happen over the coming month will help with some of that. And so hopefully some of the tools we have developed might be of use to some of you. And, finally, rethinking our frameworks, right? Sometimes we are stuck with one thing and we keep pushing it forward and we think we're on the right path, and sometimes taking a step back for a second and rethinking, are those the right hypothesis and the right thing we're looking for? I think is always a little bit important, especially when you move into a new field that moves very fast. And so, I think we need everybody, right? So I think it's a great time to be creative, whether you come from computer science, data science, stats, climate. I think there are a lot of, great problems and challenges ahead of us, and, many open questions, but also a lot of excitement, right? We are developing new ideas as we go along, and I think it's a very exciting time to be part of LEAP, and I'm very excited to be part of it. So thanks a lot, everyone.
Do you have any questions from the audience here? Yes, back.
So about the importance of picking the correct filter for generating. Oh, yeah. Thank you. So about the correct filtering to basically generate some kind of truth data for the machine to use. Do you think the correct filtering might depend on the numerical methods of the model? Like, I imagine the QV might be a sort of spectral one. Then I don't know, MIT GCM is finite volume. Then they might be different.
100%. Yeah, I actually believe that we need a good understanding of the model that we're going to plug it back in, and both the one that we developed from. So yes, I believe that there's a strong correlation between the numerics and the filtering. And that's one thing that we were able to find by doing things with different numerics and different filters. Yeah, absolutely. Yeah, 100%.
And another one. Okay, so
Again, it's the boss.
there are these filtering now. They're supposed to be commutes with like differential, say, taking divergence or something. Is one of those ones that you've tried in the field?
Yes, it's one of them. Yes, definitely.
Then is it the better one or the worse?
In between.
Oh.
Yeah, it's an in between one.
Other questions here? Yeah, Tim.
Yeah, we'll do that.
So I try to appreciate the concept of closure. And my understanding is that the input could be low dimensional from the low resolution, and the output is also the low resolution. And the closure is trying to capture the high dimensional. So machine learning, and especially deep learning, is really good at characterizing high dimensional complicated relations. So maybe you can elaborate a little bit about, you have a low dimensional input and low dimensional output, like where does the high dimensionality come in, so that what is deep learning trying to learn, what is the high dimensionality in that relationship?
Yeah, so that relationship is actually high dimensional, right? So even though you mapped it onto a coarser and lower dimension, because you're not learning the variable itself, you're only learning the kick that variable will have on the low resolution model. So that mapping is exactly kind of the high dimensional system, or the high dimensional relationship that you're looking for, except that you never go back onto the high resolution. You're only trying to capture this high dimensional relationship in a low dimensional space. And that's why deep learning is very good at it, is because the granularity of the problem is actually high dimensional.
Can the people online unmute themselves and ask their questions? Is that possible? Or can she hang?
I can read them.
Can you read them? Okay, can you just read it out so everyone can see?
Sure. By improving the performance of coarse resolution climate models with ML, are you essentially training the parameter or building better physics-based parameterization in coarse resolution model? Yeah, so that's a great question. So in this example that I showed, we're literally learning new parameterization. So we're not tuning an existing parameter of an existing parameterization. Now, other people in LEAP are tuning parameters. In our case, we didn't, but this is something we're actually doing, both with old and new, using reinforcement learning. Yeah, that's a very good question. Second question, how do you think high spatial and temporal resolution satellite observation can help improve coarse resolution climate model with ML technique? So that's a great question. I think it's going to be, it depends a little bit on the output that you're looking at. For the ocean, I don't think we have enough spatial resolution with the satellite altimetry that we have to even capture the mesoscale field. It might change in the future, very much so. Our view has been to try to use a lot of truth data coming off simulation, and then trying to see if we can bring some of the observation in by retuning, so more transfer learning or something like this. But using observation alone, again, for the ocean, it's just that we don't have enough resolution yet. That's a very good question.
Hello, Laurie. This is Eric Gao. I just raised these two questions. Thanks so much for answering these questions. I'm a student from the University of Maryland. I don't do stuff in climate modeling, but I've been doing research in remote sensing domain. So I was interested in because the goal of LEAP is to try to make the best use of satellite observations or other type of observations to climate modeling. So because in your presentation, you mainly use the high resolution climate simulation as the input, and you didn't mention any, a satellite or any other observations. So I was wondering how, the high resolution satellite observations can be used to improve the physics-based parameterizations.
Yeah, absolutely. Thanks a lot for the questions. And yeah, I mean, as mentioned, that's true. I only use data coming out of simulations. I do believe, again, for the ocean, the altimeter is probably one of the best, tools that we have out there. I'm a huge fan of it. But to capture the subgrid dynamics, unfortunately, just by itself, satellite data won't be enough for us right now. It might very much change in the future, but by itself, I don't think it's enough. I think it can complement the numerical simulation. At least that's my hope, and something we're trying to test. And I agree, I think within LEAP, it's very important to find out how we can bridge, different type of data together to improve closures.
Yeah, I'll just, this is Gail McKinley, Deputy Director of LEAP. There are other projects within LEAP that are looking at clouds, looking at the carbon cycle, looking at other things, and in those satellite data are a significant input. So there's a lot more going on in the project.
Laura, so I was wondering about the role of the atmosphere in crafting or, determining or governing the structure of some of those, some of those beautiful movies you showed, right? So, when we're considering the atmosphere only, we kind of think about of the SST as like a boundary condition, but it really does craft some of the features and clouds and the lines and the structure we see. And so my first part was, so what extent does that, should that come into play when one is trying to come up with a parameterization of the ocean? And then my second question is, when you develop, parameterizations offline and put them online, is it possible you might have like a really good parameterization, but it can't talk with the deficient atmosphere at present, and it's messing, it's making you like you're bad, but you might be better because it's tuned against a deficient atmosphere parameterization or set of parameterizations?
Great questions. So for the first one, how is the role of atmospheric forcing onto ocean turbulence? So I think it's definitely one of the drivers, right? So actually, one of my projects in LEAP is to look at LC interaction, including the turbulence part. So that's something really we are trying to push. Of course, amount of data is pretty tricky here, right? Because both the atmosphere and the ocean need to have high enough connection to actually capture that driver. So that's a great question, and definitely one that is a question mark. There are some papers out there that have been looking at the exchange between the eddies and the atmosphere and so on and so forth, especially in Gulf Stream and Kuroshio region. So definitely a lot of both scientific question, not even just on the closure problem, but just open scientific question on the interaction and the coupling. So great question, definitely one that we are planning on tackling. Now the question is, yeah, we develop parameterization in isolation, and not just of the atmosphere, right? Of all the other scales. It's a multi-scale problem. So every time we're breaking things into pieces, and I think that's one of the issues, right? You're going to talk to other scales, other pieces of the climate system, and you might be missing something super important. And so that's why what we're trying to do is to use as many type of data sets as possible. So again, some quite idealized, all the way to things that are complicated, that have more and more interactions, to see how robust we are, but also how can we capture those additional interactions that we didn't capture before, try to improve it. Yeah, it's a great question.
kind of have a clarification. Can you go back to the slide where the they haven't taken really any notes on like resolved versus like unresolved. I forgot which one it was. I mean, like it was like
Tell me more.
the one with like the red and blue dots.
Red and blue dots.
No, I mean the very simple one. I mean,
Yeah, the one
If
where
only
you
you're
said
fine.
the
Before or
zero,
after?
the popular is.
yeah, the resolved
the-
was like nearly close to zero.
Make
It's like-
up of.
Heat uptake in the.
Oh, okay,
region.
yeah, thanks.
It's,
Sorry, there are so many dots in my plots. It was my fault. Don't worry. We're getting there. This one.
Yes, this
Right,
one.
yeah,
So,
yeah.
so what does it mean? Like, what does resolve mean?
Yeah, so resolve will be, so you take your differential equation, right? And part of that equation will have a term that is what we call the advection term. So that's a non-linear term that is the dot product between the velocity and the gradient of velocity, or the gradient of temperature. And that's a term of the dynamical equation coming up from the Navier-Stokes. So that's what we mean resolve, meaning we're not coming up with an approximation for that. It's 100% on the grid, calculated on a grid. Now, everything else, all the other blue and kind of pinkish dots, all of that is not directly part of your continuous, Navier-Stokes equation. Those are approximation of all the processes that are happening that are below the grid box size that we literally came up with a closure for. Does that make sense?
And blue dots, the isopycnal and
Isopycnal, diapycnal, and eddy. Yeah, I'm not even, that's why I didn't want to explain it. It's a whole bunch of turbulent mixing processes in the ocean, vertical, horizontal, and along what we call isopycnals, which are density layers. So all the things that are below the grid box size that the model does not resolve, does not capture.
because in your paper you're talking about jets and eddies, and so I just saw those two were two types of jets and like.
Just different type of eddies contribution.
Okay.
Here. Since we're moving slide, can you go back to the
Sure.
one of the early slide that you showed 3 models and you say they have different biases? Yes, that's one. Yes, and you're saying that they show, even though they're different, they show similar biases. So one thing I want to comment on is that the word bias is different from statistics, and
Yeah,
and here the bias here is more like an arrow.
Mhm.
Because you can see it's not calculated as an average of many implementation. It could be the arrow for a particular observation, right?
So here it's an average over many years of the simulation. So the sea surface temperature average over many years of that simulation minus many years of sea surface temperature from observation.
So
What we call a climatology, basically kind of the steady state of the ocean.
So that's actually similar, but my question is that if the closure taking to the input is not all the forcing, all the process, as you said, it does not include all the forcing, then is the closure a stochastic, have some stochastic, that means that you have for certain location or for certain thing, you have irreducible error. So when you measure a particular prediction against a real high resolution simulation, then you may actually always have error, and then that error may have a different variability given different initial conditions. So therefore, when you consider metrics, you should if the projection fall within the anticipated irreducible variability, you should call that a success rather than a failure. It's just like, for example, some of the locations may just naturally have higher variability than others.
So that's a great question. So I'll try to boil it down in a few pieces. So there are different sources of uncertainty. Some come from the natural variability of the climate system, right? And so the world has many realizations. And so that's one part of, if you want, the error. And so, yeah, being able to dissociate between what's internal versus what's, coming from the missing forcing is definitely one piece. So here we're really focusing on a piece of the missing physics. Now, how much of that is random or stochastic? We're still trying to mimic turbulence, right? It's really rarely deterministic, right? So this is something we have to also take into account. They will be part of the irreducible error because at the end of the day, it doesn't matter how magic machine learning is or data science is, we only do an approximation. And so there will be a piece that is irreducible. Yes.
The metric would also, I think one of
Metric.
your paper is trying to quantify the standard deviation
Correct.
of that.
Correct.
So
So
therefore, the metric can be created.
that's correct. Yeah. So yeah, in some of our work, we do derive stochastic parameterization, and we do take into account the stochasticity as one of the error. Yeah, absolutely. Yeah, definitely a big piece.
I have actually two questions about a great talk, by the way. The first one is, I'm just asking the question also myself, like, are we being fair, when we evaluate models, right, in a sense? Because you can define as many losses as you want, and as you said, there's a zoo of them, right? And then you basically, machine learning is very clear about what is your target, where is your loss, right? So I don't know, I appreciate your thought. For instance, you could have your momentum, and then you might want to look at your TKE, and you could have like different terms and different things, different time scales as well, different spatial scales as well, right? So what do we choose, right?
Yeah, absolutely. I'll go back to my kind of semi-boring answer is we need to have as many as we need. And for different problems, you will have different targets. For a long time, I've been thinking about this idea of, seamless, simulation. Can you actually get a model that will be as good on weather timescale that will be on climate timescale, right? If you add, as many resources as you want, and, given the limited resources and the solution we're coming up with, then we're seeing that it is a very difficult problem. So I believe at the end of the day, that's where the human part comes in. It's not like machine learning where we define a loss. Here, we have to be very careful on how we define the metrics we're looking at. And again, are we targeting physics or are we targeting, say a probability of temperature so then you can make decisions or you can build infrastructure. You might not want to have the right physics, but you might want to have the right variables over a short amount of time. And I think that's where the human component comes about, is how do you frame your problem? Yeah, it's a tough one.
And make kind of really big question also related to chances. Is it just a matter of resolution? Can we just sit back, relax, wait for a few years, come back, and then everything is solved? We have some big GPUs or new TPUs.
Yeah, I mean, we all know that there are many pieces of the system that we will never resolve, right? Even if we increase in compute power, they are part of the system for which we don't even have equations. I mean, when I talk about the ocean, I always make the comment that we don't even have an equation of state. And, for the atmosphere, you have the ideal gas law, how to relate, temperature, pressure, and other things. For the ocean, we do a Taylor expansion. So, this is one of the basic properties of, of the ocean. So I think we should try it all. I think I would love more resolution, but then I can think about sea level rise around the coast where many of the processes are really, at the boundary layer scale. So, you're going to run a climate model for 100 years. I think we should go after everything. Online. Okay. So I'm waiting.
Hello, Laure. Eric Gao from University of Maryland again. So two questions. The first is based on the previous question about unresolved processes. So I understand, like for subgrade processes, the parameters are not calculated or projected continuously within the time stack. So you need to have this variables approximated. Oh, what you are doing is try to use machine learning to improve the parameterization process. Oh, so I guess you mean the machine learning based parameterization is better than the traditional parameterization. So my question is, before machine learning technique, how people develop this parameterization process?
Yeah, great question. So quite a few different ways. So I'll take, a simple example, which is mixing. So we know that mixing should happen kind of at a molecular scale. And so mathematically, it's going to be the Laplacian of the variable that you're looking for. Now we know mix, we can't resolve those scales, right? But we know that turbulence, part of the turbulence does mix. So at the end of the day, it should be diffusing stuff. So people just assume you can keep the same operator and you'll just crank up the number in front of it. So I'm exaggerating a little bit, but this is kind of one way. So trying to think about what is the effect of the process you're missing and trying to come up with a mathematical framework or representation for it. And then you always end up with a free parameter that you either try to fit with data if you have enough data and if you're lucky, or you run many numerical simulation and try to actually come up with scaling laws for it and so on and so forth. So there are quite a few ways to kind of come at it. It's really a mix between, theory, understanding of the process, and then, some assumptions about what you can do with it. And this is something, many of us, it's not a criticism of parameterization. I've developed some myself. So, this is also the way we think about it. And with machine learning, we come at it from data, we end up with something, then we still need to understand it. So even when we came up with the equation discovered one, we had to take a step back and think about it. What are the equations that we're getting? Do they mean something physically? And I think that still remains a very important piece of it.
Yeah, that makes sense. Thanks. And a second question is, so here the direction is you use machine learning to try to get some new physics and plug it into the currently existing physics models. Well, another direction is people build a completely new artificial intelligence-based network, train the network, and plug some physics into the artificial intelligence or some neural networks. So do you think this is something promising, like probably in the next few decades, people develop another new set of artificial model building up on the artificial intelligence? Like, do you think this is promising?
I mean, there are many groups that are trying, right? So I think, I think it is an exciting part of, many of the projects is how do you find the right balance between the two? I think for all of us, the jury is still out, right? We're developing new tools and new ideas, and some of them will work better than others, and some will work better to answer certain type of scientific questions, while others will answer a different piece of it.
Did Shanice have a question?
Yes. Do you know how the biases across data set influence the ML performance? How the biases across...
Hi, Laure.
Unmute. Super. Hey,
yeah. Since we're on this slide, it shows sea surface temperature biases, and it's across the board for multiple models. So when you use these high resolution data sets that have common biases, do you account for that in the your algorithm's performances?
Wonderful question. So here, definitely, it's those are coarse resolution simulation. What we try to go is for higher resolution simulation, where some of those biases or many of those biases are corrected, and we try to stay away, or we try to pick pieces of the data set where the biases are not large. So yeah, that's an excellent question. All the high resolution model that we're using are still models. So that means even though they have more resolution, they do better, they still have a lot of errors in them. Yeah, it's a wonderful question.